In a previous presentation entitled Significance of Thermodynamic Coupling Effects in Kinetic Separations, I had demonstrated that transient overshoots of the more mobile species serpentine equilibration trajectories are signatures of kinetic separations using microporous crystalline materials such as LTA4A zeolite and DDR zeolite. In that presentation, I had used 3 examples of kinetic separations: nitrogen-methane separations using LTA4A, nitrogen-oxygen separations using LTA4A zeolite, and CO2-ethane separations using DDR zeolite. In all 3 cases, I demonstrated the importance of including thermodynamic coupling effects in the analysis of transient uptakes within single crystals and transient breakthroughs in fixed bed adsorbers. My presentation today is a follow-up to that presentation in which I examine mixture desorption kinetics. I use the same 3 examples that were discussed previously and also add to that list a 4th example of desorption of propane mixtures in Shabbosite zeolite. The entire presentation and simulation details that I will present are from my 2019 paper published in Separation and Purification Technology. So let's begin the discussions with the desorption of nitrogen-methane mixtures in LTA4A zeolite. For kinetic separations of nitrogen-methane mixtures in LTA4A zeolite, the adsorption equilibrium favors methane due to its higher polarizability, but nitrogen has a higher diffusivity because the gas molecules jump lengthwise across the 4 angstrom windows of LTA4A zeolite, and nitrogen has a smaller cross-sectional dimension. The ratio of diffusivities of nitrogen to methane is about 25, and the separation is driven by intra-crystalline diffusion. I show 2 graphs here, the left showing the transient uptake kinetics for nitrogen-methane mixtures at a total pressure of 100 kilopascals, 20 kilopascal for nitrogen, 80 kilopascal for methane. And as explained in my foregoing video presentation, nitrogen experiences a significant overshoot as it equilibrates within the crystallite. Methane, on the other hand, approaches thermodynamic equilibrium in a monotonous manner. The continuous solid lines are the simulations of the transient uptake using the Maxwell-Stefan diffusion equations. Including thermodynamic coupling, we note that the transient uptakes show an overshoot in the nitrogen loading, and this overshoot disappears when we ignore thermodynamic coupling effects. And as emphasized previously, the experimental observation of Habgood, in which transient overshoots were detected for nitrogen, can only be captured by proper accounting for thermodynamic coupling effects. Let's now look at the desorption kinetics, in which the equilibrated samples containing this equilibrated mixture is desorbed by exposing the equilibrated sample to an environment at a total pressure of 10 kilopascals with 2 kilopascal partial pressure of nitrogen and 8 kilopascal partial pressure of methane. The simulation of the desorption kinetics are shown here. Continuous solid lines are the desorption kinetics determined using the Maxwell-Stefan diffusion equation, taking thermodynamic coupling effects into account, and the dashed lines are the simulations in which we ignore thermodynamic coupling effects. We note for desorption that nitrogen experiences a significant undershoot in its approach to thermodynamic equilibrium. So we conclude here that overshoots and undershoots are signatures of kinetic separations that result from thermodynamic coupling effects. You may even argue that this result could have been anticipated, but I have not seen any experimental confirmation of transient undershoots in desorption kinetics. Let's proceed then to nitrogen-oxygen desorption using LTA4A zeolite. For separations of nitrogen-oxygen mixtures using LTA4A zeolite, the mixture adsorption equilibrium favors nitrogen that has a significantly larger quadrupole moment. However, the diffusivity of oxygen is significantly higher, by a factor of about 100 than that of nitrogen, because oxygen has a smaller cross-sectional dimension and both gas molecules jump lengthwise across the 4 angstrom windows of LTA4A zeolite. I show two graphs, the left one showing the transient uptake kinetics, the right one showing the transient desorption kinetics. In the uptake kinetics, a crystallite of LTA4A is exposed to a environment at a total pressure of 600 kilopascals, containing 21% oxygen and 79% nitrogen. Taking due account of thermodynamic coupling, we note that the oxygen loading experiences a significant overshoot as it approaches thermodynamic equilibrium. Nitrogen, on the other hand, approaches thermodynamic equilibrium in a monotonous manner. If we ignore thermodynamic coupling, no transient overshoot of oxygen is realized. The equilibrated sample is then exposed to an environment at a total pressure of 100 kilopascals, 21 kilopascal partial pressure of oxygen, 79 kilopascal partial pressure of nitrogen. The transient desorption kinetics are simulated using models in which, firstly, thermodynamic coupling effects are included. This is shown by the continuous solid lines, and the dashed lines are the corresponding simulations in which thermodynamic coupling effects are considered to be negligible. We note that oxygen experiences an undershoot in its approach to thermodynamic equilibrium. Therefore, thermodynamic coupling effects induce transient overshoots during uptakes and transient undershoots in mixture desorption. Consider the separations of mixtures of CO2 and ethane using a DDR zeolite that consists of cages separated by windows that have dimensions of 3.65 angstrom in one direction and 4.4 angstrom in a different direction. The minimum aperture is 3.65. The pencil-like CO2 molecule has a significantly higher diffusivity, that is a factor 50 higher than that of ethane, that is bulkier. Here I have two graphs showing transient uptakes and transient desorption of mixtures of CO2 and ethane. On the left-hand side, the crystallites of DDR zeolite are exposed to a bulk gas mixture at a total pressure of 40 kilopascals, 20 kilopascal each for either guest species. Including thermodynamic coupling, we note that the CO2 experiences a significant overshoot in its loading as it equilibrates. This transient overshoot is in good quantitative and qualitative agreement with the experimental data that has been published by Carragher's group in Nature Communications. If we turn our attention to desorption of the equilibrated sample, we note that CO2 experiences a transient undershoot while it undergoes a desorption. And if we ignore thermodynamic coupling, the undershoot disappears. So as in the previous two examples, we conclude that transient overshoots and transient undershoots are are signatures of kinetic separations and result from thermodynamic coupling influences. The fourth example we consider is the kinetic separation of mixtures of propene and propane using Chabazite zeolite that has cages separated by 8-ring windows with apertures 3.8 angstrom in one direction, 4.2 angstrom in a different direction. The minimum aperture is 3.8 angstrom. The mixture adsorption equilibrium is in favor of propane, but due to subtle differences in bond lengths and bond angles, the diffusivity of propene is about 5,000 times larger than the diffusivity of propane. As usual, we consider both transient uptakes and transient desorption kinetics using two different models. The continuous solid lines are simulations in which thermodynamic coupling effects are duly accounted for. The dashed lines are the corresponding simulations in which thermodynamic coupling effects are considered to be negligible. On the left-hand side, we have transient uptakes from a virgin Chabazite zeolite that is exposed to a total gas containing total gas mixture at a pressure of 100 kilopascal, 50 kilopascal each for propene and propane. Propene experiences a significant overshoot in its approach to thermodynamic equilibrium. This overshoot is a direct consequence of thermodynamic coupling effects. If thermodynamic coupling effects are considered to be negligible, no overshoot in the propene uptake is detected. The corresponding desorption kinetics are shown on the right-hand side, and we note that propene experiences a significant undershoot in its component loading as it desorbs from the crystallite. Overshoots in transient uptake and undershoots in transient desorption of the more mobile propene is a direct consequence of thermodynamic coupling effects in mixture separations. The takeaways from this presentation are summarized in the slide. Transient undershoots are signatures of the desorption kinetics of 4 different binary mixtures that have been considered in this talk. Nitrogen-methane desorption from LTA4A, nitrogen-oxygen desorption from LTA4A, CO2 ethane desorption from DDR zeolite, propene desorption from Chabazite. In all 4 examples, we note that the more mobile species undergoes transient undershoots, and these undershoots are engendered by thermodynamic coupling effects. A conclusion that also emerges is that for transient desorption in fixed bed adsorbers, the inclusion of thermodynamic coupling effects is of vital importance.